And it's Thursday, it's the 15th, and, ooh, it's the Ides of April. Does that mean anything? No, actually not. I'm sorry, it's the 14th. Oh, it's going crazy. All right, so what are we doing? Arc length, we did area. We're going to do a little bit of everything, really. This is going to be sort of a summary of everything we did in vector polar, okay? Here we go. What if r is sine theta? Can you find the slope along the curve, wherever you please? How would you find the slope of a tangent line to that curve? Now remember, you know what this looks like. This has vertical symmetry. It's a circle of radius 1/2, half of this. Okay, the center is at 0, 1/2 on the y-axis, if there's a y-axis, right? So you know what this looks like. So how would you get, say, dy dx, the slope of the tangent line along that curve, when theta is, I don't know, pi over 6? That's the question. So given this polar curve, can you get me the slope of a tangent line along that curve at a particular theta value? How would you do this? Any ideas?
Well, we have to use that. Thing, power vector.
We could turn this into a vector or parametric question, right? Because if we know r, we know x and y, exactly. So let's change this to a position vector as a function of theta instead of t, big difference. And it's going to be, what's the x component? R cosine is the x component, right? So that's r. R cosine looks like this. Okay, r isn't the constant, that's all. All right, so that's the x of theta. What about the y of theta? Sine of theta times sine of theta, right, sine squared, exactly. All right, but I'm making the point. It's r cosine, r sine. Okay. Now, to get dy dx, not only do I need y of theta and x of theta, what else do I need? Dx d theta and dy d theta, because how are you going to get this? Dy dx is really d... Right, dy d theta divided by dx d theta. Okay, let's do it. So we're basically going to find the velocity vector. All right. There's a lot of ways you could write this.
So you have to use the
Product rule, good. Okay, so first times the derivative of the second, what's that? Negative sine, right. Plus the second times the derivative of the first. What's the derivative of the first? Yep. Okay, good. So that's your x prime or dx d theta. What's your dy d theta? First times derivative of the second is cosine plus, well, yeah, plus the second times the derivative of the first. Okay. So you end up with cosine squared minus sine squared, and you end up with 2 sine cosine. You could have written this as sine squared, and you use the chain rule, get the same thing. All right, now I want dy dx. How do you get dy dx? It's this divided by that, right? All right, so that's what? 2 sine cosine? Okay, 2 sine theta cosine theta over, I'm going to write it this way. How about cosine squared theta minus sine squared theta? You could write it a lot of different ways. Okay, that's the derivative of the tangent. So that's the slope of the tangent line anywhere along that curve. But I wanted it evaluated at pi over 6, was it? All right, so let's do it. What's the slope of the tangent line when theta is pi over 6? Just plug it in. So what's 2 times the sine of pi over 6 times the cosine of pi over 6? You got to know your reference angles. I bet you they'll do this to you in the non-calculator active section.
1/2 for sine and rad 3 over
2, yeah. Rad 3 over 2, right. Good. Is it the one? This is 30 degrees, so the sine is small. Yes, this is 1/2 rad 3 over 2. All right, so this is cosine of pi over 6 all squared minus the sine of pi over 6 all squared, and we get 2 times 1/2 times rad 3 over 2 over rad 3 over 2 squared minus 1/2 squared. Well, what happens to these guys? They cancel. So the numerator is rad 3 over 2. And what's rad 3 over 2 squared? 3/4 minus 1/4 is 2/4. What happens when you divide rad 3 over 2 by 2/4? Well, this is really a half. How do you divide by a half? Multiply by 2. Rad 3 is the slope there. Correct. All right, why don't we confirm all of this? Questions? Rad 3? Yes. All right, so you have a positive slope, and rad 3 is about 1.7 something. Let's see if that makes sense. Let's take a look at the graph. All right, where's my Hal? Okay, Hal, what mode are you in? Oh, you're in parametric mode or something crazy. No, you're in functional mode, but I need polar mode. Okay, there it is. And it's sine theta, right? So I should clear all this stuff for good. Oh, my God. Okay, sine theta. Ding, 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 ding. All right. And remember, you told me theta min was 0 and theta max was pi. I don't need 2 pi, right? So I might as well do that here. And I have this on purpose as pi over 24, so it's easy to trace to pi over 6 or pi over 3 or anything I like, right? So graph. And there's a sine. Yeah, that's sort of small. You might zoom in or something, I guess. I don't know. Zoom in a little bit. All right, there you go. All right, so that's a circle of radius 1/2 or diameter 1 with 90-degree axis symmetry. Now, if I trace it, I want to get to pi over 6. Now, I have this set up with a theta step of pi over 24. So how many pi's over 24 do I need to get to pi over 6? 1 pi over 4, 2 pi over 4 would be pi over 12, 3 pi over 4 would be pi over 8, 4 pi over 4 would be pi over 6, right? 4? All right, so I'm going to trace over 4. Pi over 24. That's what theta is, right? 2 pi over 24 or pi over 12. 3 pi over 24 or pi over 8. 4 pi over 24 or pi over 6. All right, so the coordinates on the circle are x is this god-awful number and y is a quarter. But look at F5, derivatives. You can get dy dx right there. Now, what do we say it was? Rad 3, which is 1.732, I think, right? Let's do it. Oh, boy, are we good at this. All right, crazy talk. All righty then. Well, that really is all review. What's new today is how are you going to do this for arc length? Can you do the same kind of argument for arc length? All right, so let's take a look at this. Remember, we know how to do dy dx in parametric mode, right? Do we not know how to do arc length in parametric mode too? We do, right? Okay, so let's do that. Let's take the same result here and find the arc length. Now again, 2020 hindsight, we know the answer. This is a circle of radius 1/2. How do you get the entire arc length or circumference? What's the circumference of a circle? 2 pi r. And here r is 1/2, right? So what's 2 times pi times a half? Pi. So we should get pi out of this. The point isn't that we know the answer already. The point is, do we know how to do it when it's not so easy? Okay? So we can check our work here because we know the answer. All right, so the answer should be pi. All right. So we'll use the same result. And how do you do arc length parametrically? We're using the same curve, but now we're doing the arc length, right? So here's the curve, right? It's that circle thingy above the x-axis with y-axis symmetry, centered at 0, 1/2, radius 1/2, the whole thing, right? There's your vector form or parametric form of the same graph. There's your velocity vector. So let's use it. All right, let's do. Remember that arc length, how do you write arc length? Arc length is the integral from, well, in this case, it's going to be in terms of theta, right? So from, say, alpha to beta. Theta min, theta max, okay? Of the square root of who? Dx d theta squared plus dy d theta squared times d theta, right? This is the same thing as we did with vectors in terms of t, but so what? It's in terms of theta. Big deal. It's just a dummy variable. Who cares? All right. Now, let's use our x of theta, our x prime of theta, which is down here. Now, let's write it the easy way. This is it. Cosine squared minus sine squared, right? Okay, that's your dx d theta. And dy d theta was 2 sine cosine, right? All right, so let's write that. All right, so this equals the integral from, what was theta min theta max when you did the area? 0 to pi, okay. And this was cosine squared theta minus sine squared theta, but we're squaring it. Oh, God. And this was 2 sine cosine. Right? So we're going to square it. How about, all right, let me write it out. 2 sine theta cosine theta. And we're going to square root that mess, and we're going to d theta it. And if it's not easy to integrate, we could always get a numerical estimate using how. But I think this actually simplifies. Square. This actually simplifies. Are you ready? Here we go. The integral from 0 to pi of humongous radical. Okay, so let's see. Let's square this. When you FOIL this out, if you multiply it by itself, you get cosine squared theta minus cosine squared theta pretend times cosine squared theta minus sine squared theta. So what do you get? Cosine minus sine times cosine minus sine. What do you get? FOIL it. Cosine squared, sine squared, cosine squared, sine squared. So that was your dy d theta. This is your dx d theta, straight from the slope formula, right?
Yeah, that's the same thing.
Same thing. I just wrote it backwards, yeah. Okay? All right, so let's FOIL this. Cosine to the 4th of theta. And then I get a cosine squared times a negative sine squared. And I have a cosine squared times another negative sine squared. So how about negative 2? Okay, so I'm going to write this way. Sine squared, cosine squared? Okay. The order doesn't matter. And then sine squared, negative sine squared times negative sine squared? Sine to the 4th. Plus this thing. Well, isn't this plus 4 sine squared cosine squared? And this is all inside the radical. Okay? What do you notice? Well, it doesn't cancel, but they combine. 4 minus 2 is usually 2. Okay. So cosine 4 to the 4th theta plus 2 sine squared cosine squared theta plus sine to the 4th theta.
You asked for 5 terms here, but you want 4 here. Is that correct?
Well, use 4 terms to estimate. And then the 5th term is your error term.
So now
Right.
this
All right. So, wait, hang on. All right, so we got to square root this. And this is a pain to integrate unless that's a perfect square that you can square root. Is it?
pretty much.
Can you FOIL that and end up with the same thing in both parentheses, is the point. Any ideas? I'll start you off.
Plus red 2.
Well, no, hang on. If, when we squared cosine squared minus sine squared, we get, wait, hang on, we get this, then the square root, then this is just cosine squared plus sine squared squared, isn't it? If you FOIL this, don't you get that?
No, you get all
Right? If you FOIL this, you get that. So if you FOIL this, you get that, don't you? All right, don't forget we're square rooting that. And we're integrating with respect to d theta from 0 to pi. Holy cow, what a mess. But it's simplifying. It's okay. Relax. It's not that bad.
How do you expect this to be
Because you can do it. All right, now, when you square root a square, you usually get an absolute value. But in this case, it doesn't matter. Why? Because cosine squared is always positive, and sine squared is always positive. So what's the absolute value of cosine squared plus sine squared? Well, it's cosine squared plus sine squared. And this is the easiest integral you're ever going to do, because that's 1, isn't it? Oh my God. What do you mean? I don't expect you to do the integral of 1 d theta. Are you nuts? Right? Cosine squared of an angle plus sine squared of an angle, that's a Pythagorean trig identity, is always 1, if it's the same angle, of course. Wow, that was hard. And so what's the antiderivative? theta. And if you evaluate from 0 to pi, you get pi. And didn't we say we were going to expect pi for the arc length of this creature? 2 pi r, r is a half. Oh boy, we're good at this. Alrighty. So, so let's summarize. Can you get me a general form for the arc length of a polar curve? Right? In other words, we know that we can do it in terms of x. We can do it from the integral from a to b, the square root of 1 plus dy dx squared dx. Remember when we started doing arc length way back?
Yeah.
And that's the arc length. All right. We also said, what if we do it from f of a to f of b, and we know the inverse function, not y is a function of x, but x is a function of y. We also ended up with this, didn't we? If that wasn't integrable, this might be for the same curve, same arc length. Then we went crazy, and we did it parametrically. From t1 to t2, dx dt squared plus dy dt squared.
That F1.
F of a, f of b.
No, down. T1.
T1, T2, square rooted dt, right? And this is sort of what we did today. We went from theta min to theta max, dx d theta squared plus dy d theta squared, right? So could we write this in terms of r and theta instead?
Of course we can.
Sure we can. All right, so let's do the same problem we just did. The same problem. We're going to do this stuff, but we're going to say any r of theta here. Not particular one, but any r of theta. We're going to redo this whole thing for any r of theta. Okay. So, if your displacement vector is r of theta cosine for the x component, and r of theta sine for the y component, that's your column vector. What's your velocity vector?
That's easy. It's the derivative of that.
All right, so,
We have to do the product.
yeah, here we go. First times the derivative of the second plus the second times the derivative of the first. Little parentheses here. Okay, that's dx d theta, isn't it?
What's the derivative of R? Oh, that's
Whatever it is. I don't know what r is. Any r of theta. I'm doing this in general. All right, differentiate the bottom for dy d theta. First times the derivative of the second plus the second times the derivative of the first. All right, there's your velocity vector. All right, from that, you can easily write dy dx. How? dy d theta divided by dx d theta. So it's r of theta cosine theta plus sine of theta, r prime, over negative r of theta sine of theta plus cosine of theta, r prime. All right, so that's your dy dx, the slope of the tangent line in terms of x and y, anywhere along that polar curve. But my question is, what's the arc length?
well, then we have to do the square root.
We have to do dx, which one's dx? Dx d theta, we'll do it here. Dx d theta squared, you tell me, dx d theta squared? How do you do the arc length? How did we do the arc length? Dx d theta squared plus dy d theta squared in a square root d theta from theta min to theta max. Okay, good. Let's do that. Well, we don't have to. Well, yeah, you could do that, but it turns out that's more complicated. You're going to like this way because it's going to come out easy. Ready? All right, so let's do that. The arc length is now the integral from theta min to theta max of the square root of dx d theta squared plus dy d theta squared d theta. And dx d theta was, where did I put it? Here. Okay, so that's going to be the integral from alpha to beta of, okay, dx d theta is r prime theta times cosine theta minus r theta sine times the sine of theta. I just wrote it backwards. We had a negative r sign in front. I just wrote it backwards. I like the negative in the middle. It doesn't have to be. Now, I'm running out of room, so plus stuff. All right, here's dy d theta squared. It was r prime of theta sine of theta. Believe it or not, this simplifies nice. Plus r of theta cosine of theta squared. And we're going to square root this whole humongous mess, d theta. And this is not really kosher from notation, but you get what I mean. This is all one line, okay, inside the radical? It's not very kosher, no. But it doesn't fit, okay? All right, so.
So wait, you have to divide?
No, it's not dividing. That's the point. This is one big line. Yeah, don't get crazy. Thanks, Patrick. With friends like you. All right. So let's square this crazy mess. Holy mazzoli. Again, we're going to do that FOIL thing, right? So it's going to be this thing squared. Then you got this times this, and another this times this, and this thing squared, right? Didn't we do that before? All right, let's do it. It's the integral from alpha to beta of humongous radical, okay? So it's this thing squared. Okay, so it's r prime theta squared cosine theta squared. Okay, minus two of these guys, right? So minus 2 r theta, r prime theta, cosine theta, sine theta. Holy crap. It goes on and on and on, my friends. This is the song that never ends. Okay, plus r theta squared. Holy crows, sine squared. Plus this thing squared. Holy jeez. Okay, so plus this thing squared. All right, so this thing squared. R prime theta all squared. Right? Sine theta squared. Plus 2 of these. Plus 2 r theta, r prime theta. So it's not so bad, right? Do you see why? What happens? This cancels just like last time. Plus r squared theta, cosine squared theta. D theta is outside, okay? It's not so bad. This and this cancel, right? And then you have r squared theta sine theta plus r squared theta sine squared theta. What's that? Does that simplify? R squared sine squared plus r squared cosine squared. Doesn't that simplify? To 1 times r squared, right? If you factor out r squared to get cosine squared plus sine squared, or sine squared plus cosine squared is 1. So this is just r squared. What's this?
Wait, why is that just on r prime squared?
R prime squared. So you're done.
Wait, I missed that step.
Oh, well, you're screwed. Look, this is gone, right? This middle stuff? Okay. If these two are, if you add them, you can factor out the r squared. What's left?
Oh, and then that's 1.
And that's 1. Same thing here. You can factor out the r prime squared, and you're left with 1. So, ta-da, done. Holy cow.
So now you want to make it.
You don't have to do it that way, but realize you can. If it's easier to do it the way we did it, go for it. That's as simple as it gets, unless you know what r is itself. Then you plug in r and r prime, it might simplify further, which it did in our case. Okay, so guess what? That's all she wrote.